All right. Thank you, everybody. I'm going to talk about rank regression for continuous outcomes. It's rank-based. If it works for continuous outcomes, it should work for any orderable outcomes. But I focus on continuous because that's the least developed direction. And I want to make sure everything works for continuous outcome. Right. So, many statistical methods are sensitive to outliers, to distributions, and they depend on the scale of the outcome. These are both three of common reasons for people to develop alternative methods like rank-based method, because many methods are sensitive to trim values and depend on the scale outcome. All right, the rank-based method, you can tell, you learned quite a few of them from textbooks like Wilcoxon's test, pyramid correlation, Kurzweil-Wallace test. But after these, almost nothing's done beyond these methods. Rarely things that talk about, let's say, for regression, or any other method, rank-based. So what we want to do is rank regression with all kinds of covariates and with all kinds of types. So a very general framework. What we want to focus on is regression methods that only deal with the outcome ranks, so that you can do a transformation on the outcome as long as the transformation is monotonic. The model essentially is the same, and essentially is the extension of Wilcoxon's rank sum test. This is analogous to linear regression versus two-sample t-test. In the literature, you see terminologies like nonparametric regression, semiparametric regression, and quantile regression. All these are not rank-based. In nonparametric regression, the left-hand side is the conditional expectation. So it's dependent on the scale. If you do a transformation, the expectation will change. And the right-hand side is very flexible. In semiparametric regression, the right-hand side is also flexible, but with a clear structure. Like there's a parametric portion of it, and there's a non-parametric portion of it, as in the monotonic single index model. And quantile regression focuses on the quantile of the outcome, but they directly link the quantile to a linear combination of the predictors. So the scale is also involved, it's relevant. So all these methods depend on the scale of outcome. And what we want to do is really scale-independent approach. Rank-based approaches are often quite robust. And here is a quick example. Here we simulate two sample data, sample size 100, two groups, and if x is 0, then y follows the normal distribution 0, 1, and if x is 1, y is follow normal distribution with the same variance but the shift with 0.5. So this is a perfect scenario that we can do t-test because everything is satisfied for t-test. And of course, if you do t-test, you get power that's a little higher than Wilcoxon's rank sum test. That's expected. However, if your data is not as perfect as this, there's some hidden transformation behind it. And here, just for example, I just use exponential, then your power may suffer. Well, in this specific example, because it's exponential, you can certainly try to plot it and realize, after log transformation, you could do the perfect t-test. But in real world, transformation may not be as elegant as this. Maybe just something is hard to decipher what's the inverse of it. So we have a dilemma that if you use t-test, you really can have a maximum gain if everything is perfect. But if something's wrong, you may just have a power loss. It's really unfortunate in textbooks that this column has been emphasized a lot. Then whenever we teach rank-based method, we emphasize that, it's a little less efficient because in ideal situation, there's a perfect approach, and perfect approach is always more powerful because it's ideal. But this column is rarely mentioned or mentioned in a sentence, in passing, and it's at least very little emphasized, to the point that many students, including me, when I graduated, I got a message from this column. I felt that rank-based test is just something that it's out there. You may want to do it, but linear regression is all t-test is always better. Well, this kind of thing actually is quite prevalent. For example, I taught 510 in the summer, and I got slides from previous instructors. And this is one slide comparing parametric versus non-parametric. And about parametric is stated this way: it's always preferred because these are more powerful, more efficient. If it's always preferred, why do we bother teaching non-parametrics? The real world, the real message should be it's efficient and powerful if the assumptions are correct. But that's a big if. And it's rarely emphasized. There's a big if there. But it's sensitive to outliers and skewness of distributions. In fact, because of simulations like this, if you ask me to choose between t-test and Wilcoxon test for the rest of my life, I would go with Wilcoxon for sure, because I know, the power loss I have is small, but the power gain I have, compared to some other, would be huge. In other words, the gain of t-test versus Wilcoxon is just a little bit more if everything's perfect, but the potential loss is large.
Chun,
yes.
Just to maybe make a comment that if I change your simulation and increase n to really large, how would that power change differ?
Well, if the effect is the same, n gets bigger and bigger, then power is approached to the 100%. Then the power difference gets smaller and smaller. Yeah. But if it's this small, then it's different. Yeah. All right. So for the rank regression, it's essentially you see it looks like ordinal data analysis, at least one version of it. So I'll spend a few minutes on ordinal data analysis so that you are familiar with the language in the model and it's easy to carry over to continuous outcome. A special case of ordinal data is binary data. It has only two categories. Often we denote it as 0 and 1, and we can use category 1 as the outcome of interest. The probability, we can compute the probability as conceptually and odds. And probability and odds always go monotonic. The higher probability, the higher odds, the higher odds, the higher probability. And for binary outcome, we often use logistic regression, in which we fit the log odds as a linear function of predictors. And in logistic regression, because the outcome is binary, basically your model just gives you the two probabilities given the covariance. You just put the probabilities there and multiply them, and that's your likelihood. You maximize it to get MLE. When we have ordinal data with more than two categories, let's say K categories from C1, C2 to CK, if we want to keep the ordered nature, we can dichotomize the outcome in K-1 ways. You can dichotomize here, or here, or here. There are K-1 possible ways of dichotomization that respect the ordered nature of the data. Then you can fit K-1 logistic regressions, say. Here we will have a K-1 intercept and K-1 coefficients. Here, the effect of X is going to be reflected in multiple parameters. And this is a little awkward to interpret. And sometimes when you fit data, you can see for some data, these beta are actually quite similar. So naturally, you may want to just put that as a condition. You require the same beta for all the X's, no matter where you dichotomize it. So this is called ordinal logistic regression. Here, we still essentially consider K-1 possible dichotomizations, but leave the beta to be the same. And in short, we can write it as a single line like this. And here, because of the constant beta, the alphas has to be monotonic increasing, because here we model the left tail of the probability. As the category increases, the probability increases. So here has to be reflected here. All right, this model is easier to interpret because now effect of X is a single number, no matter where the dichotomization is. And E to the coefficient can be interpreted as the ratio of odds for the outcome to be in a higher category when there's a 1 unit increase of X rate. And notice now we have a negative sign Before this, we just use plus signs. The negative sign here is because the model is on the left-hand side is the model left tail. So we want, if beta is positive, we want an increase of x to correspond to increase of y. So the y should have more likelihood to have a higher category. But here we model the left end, so that's why this has to be lower if x is higher for positive beta. So that's why we have negative sign. In this model, you can write down all the alphas together as a vector, as a profile, and then there's a shift, right? That's a log off. Or you can take exponential of this, and so you have a baseline off for every possible dichotomization and times the constant. And that constant depends on covariance. And because of this property, this model is called proportional odds model, because the odds per profile is proportional to each other from one person to another person. And all this because of the constant beta. And this model is also called proportional odds model, and the constant beta assumption is called proportional odds assumption. And certainly, I have motivated everything using logit in logistic regression, but you can replace that function, link function, by any other link function as long as the inverse CDF is a quantile function of a continuous distribution. For example, these are the common 5 choices for ordinal data analysis. Logit, which is the inverse CDF of logistic distribution. That's why it's called logistic regression. It's also called proportional odds model. You can replace it by probit, and this, the practice started in the 30s. People analyze ordinal data using probit link, and there's some other link functions. C log log corresponds to the proportional hazard model in survival analysis. The likelihood is actually quite simple. It looks ugly, complicated, but because it's ordinal nature of the data. Basically, the model gives you a multinomial distribution for every covariate, for every person. So, and you observe a specific category, then all you need to do is put down the probability for the observed category for that person, and then you multiply all together. Here I write it this way: is if these are all the likelihood for those who have the lowest category, and this are the likelihood for those who have highest category, and for all the others in between, you have to take the cumulative probability minus cumulative probability for lower category. All right, so these are just straightforward, just product of all the probabilities. A nice property of ordinal data analysis is there is a latent variable interpretation. That is, you can imagine your ordered data, ordered categorical outcome really comes from a latent variable that's continuous, just you didn't observe it. And that continuous variable is called Y star. It's nicely related to the predictors in this nice linear model way. And it's related to the outcome in a function. It's like this. It's just your intercepts are the k minus 1 alphas, and this is your latent variable. And you have here, for example, there are 4 alphas. The 4 alphas serve as thresholds, as cutoff points, so that after applying the cutoff point values, you get 5 categories, the 5 ordered categories. And if this model is true, then naturally you can derive this property. So ordinal data analysis, ordinal regression has a very nice interpretation that has a latent continuous variable, and all the intercepts, those alpha k's, are the cutoff. All right, so now we have all the knowledge about ordinal data analysis. Our goal is really to analyze continuous data, but do it in the right way, so that no matter how you transform the outcome, as long as more than one transformation, the model is effectively the same. Well, naively, what you could do is just to dichotomize it. That's actually common in practice. Whenever they deal with an outcome continuous, it's hard to find a transformation. It's very skewed, or there's some other weird pattern. People tend to dichotomize the data and then treat it as binary outcome. So you could do it. Let's say we dichotomize at the median. We can fit the model like that. It's certainly not efficient, because once you pick a cutoff point, all the values on this side would be treated as the same value, and all the value on this side would be treated as the same value. Certainly, it's not efficient. To gain efficiency, you could instead of dichotomize it, you categorize the outcome. Let's say you pick the 3 quartiles and categorize it. Then you have an ordered regression model, ordinal regression model. And then model 1 is a submodel of model 2, and the beta are the same interpretation. And model 2 give you better estimate of data because it takes account of more information. If you want to gain more efficiency, you can certainly categorize the outcome into 5 categories, 10 categories, 20 categories. And the most extreme situation would be you treat every observed outcome, as long as they're distinct, as a ordered category. So this is essentially treating continuous outcome as ordinal. All right. So on the model side, essentially what we do is to model all the quantiles. And we call it cumulative probability model, CPMs. So you have the potential all possible quantiles of outcome given X, and you have a link function specified, and you let it to be a function like this. And here alpha is unspecified. All we need to require is this monotonic increasing function. And beta is just regular coefficient. And by the way, we just write it beta X this way, like linear regression, but this side, you really can throw in anything like interaction, spline, and all those kinds of things that can generate design matrices, you can throw here, right? So alpha is just nonparametric. And here in this model, the whole distribution is small. In this model, CPMs are semiparametric models because there's a parametric component and there's a non-parametric component of it. And it's rank-based because all we model is this cumulative probability. So it's purely rank-based. And it's the extension of the constant rank sum test. All right, so I have motivated this model from purely ordinal data approach. There's a very different motivation of the same model, which initially look quite different, but they end up to be the same model, which is this. It's called the linear transformation model. So remember, when we analyze data, if the data is not perfectly normal, just some skewness, all we may just want to do is log transformation, square root transformation, some ad hoc transformation we choose. And hopefully after transformation, the data will be more well-behaved, the model will be more robust, right? That's one approach. Or if you want to be more sophisticated, you may just go to Box-Cox family and try to estimate the distribution from that family. But that's still a family of distributions indexed by a single parameter. We don't know what's the true transformation. We just wanted to have a better transformation so that after transformation, it behaves better, okay? But what if we push it further? We want to estimate the distribution, the transformation. So here's a linear transformation model, basically to say that here's the latent variable. The latent variable will behave very nicely, connect with the predictors in a very nice way. And the latent variable connect to the observed variable in the monotonic transformation. So it's often, and it's unknown, although it's all we know is the monotonic increasing. And this is called the linear transformation model. If you keep H to be non-parametrically estimated, is semiparametric LTM. It turns out these two models are the same. It's hard to see it because they seem to have very different motivation, different direction. But actually, I already talked about ordinal data regression. We talk about the model, ordinal regression model in this format. We also talk about ordinal regression model in this format. Now you see, I motivated continuous outcome regression, rank-based regression in this format. We call it CPM. In this format, we call it LTM. And it's easy, it's not hard to prove they are equivalent. That is, if this is true, then you can prove this side. And if this is true, you can prove it. But just from this diagram, you can see, there's the connection. There's the equivalence between these two models, even though it's still hard to imagine that these two turn out to be equivalent. All right, so now I told you they're equivalent. It's just a quick summary of what they are. So one format of this model is this way. It's like traditional ordinal data regression. One format is called linear transformation model with a latent variable and with a unknown transformation. It turns out in this model, in the first model, G is specified and alpha is unknown. The intercept function is unknown. The beta is unknown. In this model, you have to specify the distribution of epsilon because to compensate for there's unknown transformation. This part you have to provide a little bit more information here. It turns out, and beta is unknown and H is unknown. It turns out that G is just inverse CDF of that epsilon CDF. And alpha, the intercept function, is just the inverse transformation for this. In other words, alpha is the transformation from the observed Y to the latent Y, so that after transformation is perfect linear model. So alpha, that intercept function, is just this required transformation. And that alpha function is the baseline. In proportional hazard model, we talk about baseline hazard function. And here, essentially, if you use a C-log link function, you would have a baseline log hazard function. If you use loaded link function, you would have a baseline log off and probate baseline normalized model of value. And beta x is the median. If the G is the link function is symmetric, and beta, essentially, if you dichotomize this data, analyze it, essentially you have the same beta interpretation as long as you use the same link function. And the choice of G, here we specify G, and we also specify epsilon, depending on which one you think about. The choice of it determines the shape of the distribution of the latent variable, or the shape of the distribution of the residual variable. All right, so that's all about the model. Now, estimation. How do we fit it? We fit it using NPMLE. For example, we have n data points. Yi is a scalar, one-dimensional outcome, and this is a vector predictor. And let's say there's no tie. Oh, this can be relaxed. Suppose there's no tie because it's easy to explain. And the index is already ordered with respect to the outcome. Right. So here's our model, and it's going to be non-parametrically estimated. So the focus will be on those n points, and we will have a n-1 cutoff, the n-1 intercept to estimate, and we also need to estimate beta. This is non-parametric likelihood. This is a generic way of writing likelihood. As long as you don't want to specify any parametric family for the distribution, you write down likelihood this way, which is CDF up to observed value minus CDF up to observed value left limit. So, and you allow all possible distributions. And this is reduced to something like this. And look at this. This is essentially multinomial likelihood. So this is essentially why we treat data as if ordinal. And the result is a NPMLE for all the intercepts and for the coefficients. And there are ties. When there are ties, the NP likelihood can be also similarly expressed. The great thing about this is the parameters are uniquely estimated. Here, think about it. If there was no tie, there were only n data points, but we have n-1 parameters here and quite a few more parameters depending on how many x's you have. So we essentially have potentially more parameters than the number of observations, but it turns out that they can be uniquely determined. We have so many parameters, there's issue in computation. It turns out that the likelihood, if you want to do a second derivative algorithm to iterate to get the estimate, you rely on Hessian matrix. It turns out the Hessian matrix has this structure that is tridiagonal, and all those white cells are zero. And for this tridiagonal matrix, there's a way to quickly compute this, to efficiently compute this inverse, so that we can do this second order Newton approach. This has been implemented in a package RMS, in a function called ORM, stands for ordinal regression model. It can deal with 10,000 categories easily. And this package is maintained by Frank Harrell, who was my chair at Vanderbilt Biostat. He's still there. He maintained quite a few packages in R. All right, so now with all this background, what's the comparison between linear model and random regression? Let's say we have a linear model. This is a perfect setup. Y equals intercept beta x plus epsilon. It can be converted this way, which is the transformation y minus intercept divided by that sigma squared. We don't know those, but you can imagine there's a transformation. And after transformation, it's going to be like this. And here epsilon follows as 0, 1 normal distribution. And this is a typical linear transformation model, and which is equivalent to a CPM. We laid it out this way. In this model, we only can estimate gamma. We can't estimate beta 0 or sigma squared, because beta 0 and sigma squared are already absorbed into the unknown transformation, because we allow the transformation to be unknown and has to estimate that. So the intercept is absorbed into it, same as the sigma squared. But still, we can compare these two models. And the result actually turned out to be similar to the result we saw between t-test and Wilcoxon test. Here we simulate data under perfect situation for linear regression. 2 axes and 3 coefficients, one intercept, 2 coefficients, and normal residual. And sample size 100. And I evaluate 2 situations. One is essentially under alternative, the other is under null, with only intercept there and coefficient 0. But you can see, we will have a little bit loss of efficiency. That's expected because it's rank-based. And here you see there's actually no power loss. I think it's just an artifact because under the null, there's a little slight inflation of the rank-based approach than the linear model. So that probably carried over to this side. So if we had done a calibration of p-values, this probably would have a little bit power loss for rank-based analysis versus linear regression. However, if you do a transformation on the outcome, and here just for demonstration, I do a simple transformation. If you analyze data like this, you probably can do a log transformation and then and do perfect linear regression. But in reality, we don't know what the transformation is. It may not be as elegant as this. But anyway, just for demonstration purpose, if I analyze Z as the outcome and fit linear regression, you can see there's power loss here, there's efficiency loss here. That's really expected. And the same message basically that there's a potential gain if everything is perfect for linear regression versus rank regression. But the potential loss is also huge. It's actually even potential more loss than the gain. So this demonstrates the robustness of rank regression. All right. So as I said earlier, that rank regression, even though we focus on continuous outcome, is really for any possible orderable outcomes. For example, here's the comparison between rank regression versus linear regression versus ordinal regression and versus regression for survival data. Between rank regression and linear regression for continuous outcome, in the models that with a known transformation, for example, if we fit a log linear model, is basically we assume there's a known transformation. It's essentially a special case of rank regression, and Cox transformations are a special case. And here the necessary transformation can be estimated instead of specified, so it can be non-parametrically estimated. So it's really cool. Well, to compensate for that, if transformation is unknown, we have to estimate that. We have to specify the distribution for the residual. So that part is for the purpose of compensating for the unknown knowledge on this side. Between rank regression and regression for binary or ordinal data, we already said that the essential rank regression is extension of that. It covers it. And when a continuous outcome is dichotomized or categorized and fit with ordinal regression, then rank regression has the same coefficient. So it's the same interpretation and it's more efficient. For survival analysis, rank regression, the actually proportional hazard model is a transformation model. Actually, the whole line of research on transformation model started from Cox model. So Cox proposed this proportional hazard model in 1972, and a year later, researchers found out that's essentially a transformation model, and there's a way to write down likelihood so that the likelihood reduces to Cox partial likelihood. And after 10 years also, people develop a general rank regression model, but using that type of likelihood, it turns out to be not efficient and computationally not good. So it's died out. But the line of research of transformation models basically have been kept within the survival analysis community, to the point that outside that community, we basically didn't know what's going on. And it's hard to know their papers. They all use this counting process language. So you have to understand those languages to understand what they're doing. But basically, proportional hazard models are transformation models with the C log log function. And there's another popular model in survival analysis that's called AFT, accelerated failure time model. They're just log linear models, and they're also a special case of LTM. Right. So, give you an example. So here is one data set I downloaded from UCI machine learning database. GEM stands for General Matrix Multiplication. So it's really trying to multiply huge matrices. There's a strong need for doing that. The whole deep learning community rely on matrix multiplication. Google developed their own chip called TPU, tensor processing unit. It's really designed specifically for matrix multiplications. And NVIDIA, the manufacturer for GPUs, they also recently, in the last 3 or 4 years, added TPUs called tensor processing units in their GPUs. There's also, those are hardware specifically designed for matrix multiplication. Matrix multiplication is heavily needed in deep learning. And here, researchers did this. They have an algorithm called SGEM that's specifically designed for GPU. And the algorithm has 14 parameters. They enumerated all possible combinations of 14 parameters. So there are 241,000 possible combinations of those parameter values. And they run 4 times for each combination. So the sample size is this, and with 14 predictors. Well, we fit rank regression on it. And the outcome is very skewed. It runs from 13 milliseconds to 3.4 seconds. And skewness is nearly 4. You know how skewed it is? Exponential distribution is quite skewed, and the skewness is 2. And here, skewness is almost 4. So it's very skewed. So here, these are the results. Here is the, we did 3 different ways of fitting the model, but they all give you the same transformation, the alpha function, intercept. And this is the 14 coefficient estimate. They all agree with each other from the 3 methods. And the bottom 2 plots are just their standard deviations, standard errors. All right, let's look at this. This is the estimated transformation. If you had used a log transformation on the outcome, it would be like a straight line, because this log scale. So it will be a straight line. So you can see the estimated transformation somehow the middle part will agree with the log transformation. But if you had used log transformation on this data, you would miss out on the left end or right end. There will be not a good fit on the 2 ends. But the middle part is roughly log, so here roughly linear. But here, this is a demonstration of rank regression on real data. Another interesting example, I haven't done it, but it's an interesting thought process, which is in gene mapping studies. For continuous traits like BMI, there is a recent trend that they transform the outcome to a perfect normal data. Basically, it's like in a QQ plot. You have outcome that's skewed, BMI, let's say, and the transformation basically is say, okay, this is, if you have a 1,000 data points, this is going to be given a value that's the 1,000th quantile of normal distribution. And this is a 2 out of 1,000 quantile, and 3 out of 1,000 quantile section. So after transformation, if you plot the data, it's perfectly normal. And they use that perfectly normal outcome, marginally perfectly normal outcome as an outcome and fit linear regression. I don't know the motivation of it. It's just you coerce data to be perfectly normal. But they could do rank regression. Look at the structure between these 2 models. Here, they force a transformation. And here we can estimate the transformation. I haven't done it because it involves a lot of computation and evaluation. It might be that for BMI, their way of forcing the transformation may turn out to be good enough. But we don't know. We have to do it and see what happens. But here certainly is one direction of application. We have a rank regression model. If we have a rank-based residual, then we can do a lot of stuff after post-model fitting. It turns out another line of research we did in the past fulfilled that. We developed probability scale residuals originally for the ordinal data. Because we focused on ordinal data, we wanted the residual to be rank-based. Right. So this definition is actually quite simple. You compare your outcome, observed outcome, with a fitted distribution. So fitted distribution is F. You compare them. Basically, you look at how many categories. What's the probability of the categories below the observed? And for those probability, you assign score 1. And what's the probability for those above the observed? And you give them -1. And for those tied with the observed, you give score 0, and you put them together. So this would be just that. And we call that probability scale residual because it's essentially the function of probabilities. We did that initially for ordinal data and extended it for all orderable outcomes. And Eric picked up the steam now work on all censored outcomes. With the rank regression, with the rank-based and with the rank-based residual, we can do quite a few things. For example, we did test for rank correlation after covariance adjustment. We did partial Spearman's correlation between the within clusters rank correlation. And I'll also give a talk on rank ICC this year in PSN. Actually, this whole research started with this paper. We wanted to define partial Spearman correlation. It turns out Spearman correlation came out more than 100 years ago. And partial Spearman's correlation has been used decades ago. But the definition people use it is really is no justification. They basically grab the formula for partial Spearman's, partial Pearson's, and then swap all the Pearson's correlation with Spearman's correlation and hope it works. It doesn't work. So I was surprised that we were the first. The formula defined partial Spearman's correlation. Really, there was no real definition of it. It's just mimicking. And for this to do that, we needed rank regression. That started the whole research of rank regression. Here's another example for model diagnostics. This is a data set from Latin American, nearly 5,000 people living with HIV. They started with the ART, antiretroviral therapy. So our outcome is the CD4 count 6 months after the initiation of therapy. And our X is just a bunch of regular ones. I highlight treatment class and baseline native CD4 because we use them in demonstration. All right, we fit logistic regression essentially, but from continuous outcome, so loaded CPMs. You can see this is for demonstration that if the model doesn't have native CD4 count as one of the predictors, the residual, the PSR, our residual versus the square root of native CD4 would have clear trend. So once you add it in, the trend is gone. It's hard to see because there are so many dots. We added a smooth curve so to show the trend, because otherwise it's just many dots. Alternatively, we also computed another residual because CPM has a latent variable scale. So you can just compute observed versus expected on that scale. It's like a linear regression residual. And here is similar result. Without that X variable, you see trend. When you add that variable in, the trend is gone. The model can be checked because we have a specified link function. That link function essentially corresponds to proportional feature. The feature could be anything. could be hazard function, could be odds, could be some other things, but we specify it. But you can check whether that specification is good. This procedure is essentially the same procedure that people use for survival analysis when checking the proportional hazard model. Basically, you can stratify your data into a few groups by X, and then empirically estimate the CDF for each group and plot the CDF after the link function transformation against Y. If, and here in this picture, there are two groups, but you could have multiple strata. There should be constant shift. So if you see constant shift across groups, that indicates that the link function is adequate. This actually is the procedure people use for checking proportional hazard model in survival analysis. One beauty of this method of rank regression is this. Initially I motivated, we want to do a rank-based regression. So, but the model ended up to model the whole distribution. Because the model gives you the whole distribution, you can do a lot of stuff. Right? We can perform evaluations on various aspects of it. For example, we evaluate the mean as a function of the age. So we let age change, but fix all the other covariates by their typical values, like their median values or their baseline values, only let age change. And then we look at the fitted mean outcome. Here outcome is what is a CD4 count after 6 months. You can see the profile, and we also compare with box cost for this situation because we talk about mean. For median, we compare with median regression. You can also focus on a specific tail probability, how it changes with age. And for that, we compare with logistic regression. You just cut off data based on that cutoff and do logistic regression. And for logistic regression, you can see they are really less efficient. Their confidence span is quite wider because they lose information by dichotomization. And there's also a blip. I don't know why is that. And similarly, you can do this for categorical predictors. For example, treatment class has 4 categories with 3 major ones and all the other lump sum together as other category. So 4 categories in this analysis, you can evaluate their corresponding outcome as a function of the specific category in treatment class, and also give it confidence band. And again, for logistic regression, the confidence band will be much wider than rank regression. And for these two, they seem to be similar, slightly wider, but more similar. So we can do quite a lot of post-regression summary because the whole distribution has been estimated. Right, here's one application of this to detection limit data. Detection limit is natural, it happens everywhere. Oftentimes there's lower detection limit, but sometimes there's also upper detection limit. Detection limit, after detection limit, what you have is a mixed type data. You have some observations observed, but some censored. All you know is below a certain threshold, but you don't know where it is. Right? So it's a mixed type data. It's censored data, essentially. And detection limit can vary over time and across sites. And here's an example. In Latin America, again, 5 countries and many study sites. These are Peru, Mexico, Chile, Brazil, Argentina. And here, what we plot is the most frequent detection limit for that year for that site. So you can see they change it. This is the most frequent. So from 40 to 80, it just happened for that year. 80 was the frequent cutoff detection limit. It changed a lot, and it's vary from time to time and from site to site. All right. For this kind of data, rank regression is perfect because rank regression only care about ranks. They don't care about specific values. However, we still have censoring here. We need to deal with it. And the way we deal with is quite natural. It's like what you do in survival analysis. In survival analysis, if something is censored, you just let the weight shouldered by all those observed beyond the censoring point. This is called redistribute to the right. That's how it works in survival analysis. And here, what we do is essentially the same thing. And this diagram shows the example. Let's say we have a data with those solid dots are observed. There are 17 of them, and there are 6 censored and 4 censored by lower detection limit and two by upper detection limit. For example, for this subject, is censored here. We know there are two observed below it. So we just use those two to represent this observation. And here we use those three to represent it. And here we use those five. And this one, because it's beyond the last one, we use nothing. Basically, this will be thrown out. And this is consistent with survival analysis. If you have censored at the last, there's no observed event beyond that, then that subject is basically lost, basically thrown away. Right. So the likelihood is going to be the NP likelihood is going to be 1 for this person. This doesn't contribute anything. And this is cut off at 2, so it's alpha 2 for that one. And this cut off 3, so alpha 3. This is cut off 5, so alpha 5. On this end, cut off 13, so alpha 13, cut off 15, alpha 15, and cut off 16. There were 17 observed points, so there were 16 cut offs. All right, so these are the likelihood for the censored, and the likelihood for the observed is just the same as the old likelihood. So you have a very similar structure of the NP likelihood, and the corresponding Hessian matrix is still tridiagonal, so the algorithm can be still efficiently run to get estimates. As I mentioned, this is double censored data. This is censored. Actually, this kind of data has been dealt with in survival analysis. It's called double censored. Unfortunately, the way they address this problem is inefficient. I think the problem is current survival analysis is heavily rely on the language of counting process. And in counting process, it's bidirectional. It treated the right censoring in the old way. It treated left censoring as it is at risk. It's different from on the right hand side. So the at risk treatment is different from our treatment here. Our treatment here is essentially it's on this end. It's just treated this way. On this end, it's treated that way, but essentially same type of treatment. But in counting process language, it's different treatment from the left censoring and right censoring, and that contributed to inefficiency. All right, asymptotics. We prove asymptotics. This is turned out to be hard. I didn't prove it. My collaborator did it. Basically, there's a challenge because the alpha intercept function is unknown, is estimated, but this has, possible value of that is going to be from negative infinity to positive infinity. So because of that, it's hard to prove anything that's uniformly consistent. So what we do is we can just choose a lower bound and upper bound, and you can choose them far away, and then you clip them, you censor them, and then you fit the model on the central data. So this approach would be a slightly different approach, but for this approach, we can prove asymptotics. Every time we prove asymptotics, there are two things. One is consistency, one is asymptotic distribution. So consistency is the first one, asymptotic distribution the second one. Unfortunately, here it's not going to be a asymptotic distribution, it's going to be a process. And the language of empirical processes will be used a lot. But anyway, at the end of the day, we can show that asymptotically, our estimator achieve a semiparametric efficiency bound. That means basically it's as efficient as you can get asymptotically. All right, so there are three conditions. Those are nice necessary conditions, but natural conditions. I'll skip those. All right, and then we did evaluation to see what's the impact of censoring. If you censor some out on both ends, would you have a lot of change in your parameter estimate? It turns out that you can just really throw away 10% of the data, you still have almost same fitted model. So because of time, I'll just skip this. If you have 1% censoring, it's almost nothing. Right? There's one thing out there that's called single index model. If for those who are familiar with single index model, you can tell that the model looks similar to rank regression, but everything is put on this side. This is semiparametric because there's a parametric part, non-parametric part. But here in single index model, beta is not uniquely identifiable. In CPMs, beta is uniquely identifiable. Here's the two ways of showing that. In single index model, essentially we will assume this. In CPM, we will assume this. The similarity is there, but the transformation is on Y here, and here transformation is on this. Right, this is just a brief history of what's going on. If you're interested, I can elaborate. But otherwise, thank you for listening.
That's excellent. Any questions? Thoughts, comments? So what's the barrier to having this become the universal way we estimate
Software.
to software?
Yeah. Survival folks, they actually did something, but they seem to, those people who heavily focus on theory, they seem to don't care about software. But software is really important. So that's why when we came into this picture, we came here. You can see for continuous outcome, basically there's nothing in 30 years, and we came in. And we didn't know much about it. We knew some, but really the language is the barrier, a lot of counting process stuff. So software is important. As I said, there is software. Frank Harrer developed it. Frank Harrer really wanted to push this. Initially, he actually advocated it almost 20 years ago, but he didn't give us enough justification why we want to do this. So we didn't do it until we felt there's a need. So the software is called RMS, and ORM can really do it. There are some other ordinal data analysis software package there, but they don't calculate variance covariance matrix for the parameters. And we do need variance covariance matrix for the parameters to do inference, to do downstream inference, like plotting constant span, things like that. And there are many parameters, so to calculate that would be a huge task, and he managed to do it in his package.
So in many ways, I mean, this should be the first step to approach data, because you can look at the estimated distribution and say, okay, if that looks normal that I'm estimating, then I should go use linear models, because I might get a slight increase.
Oh, yeah, well, that's
better.
double dipping a little.
Yeah, but yeah.
Okay.
What about your variances? If your outcomes have different variances?
The variances of parameter estimates?
No, of your Ys.
Well, no, it's just absorbed into transformation, because the unknown transformation, you can just do a scaling. So variance is absorbed.
No, I'm thinking in so we use rank sometimes when we have beta distributed outcomes, which are between 0 and 1, right? And not normally distributed.
Yeah.
But they have different variances where they are along the 0 to 1 scale.
Oh.
So I'm saying the Ys are not, normal 0 sigma squared.
Oh, that's interesting. If you have
They have a sigma squared.
an outcome that's naturally bounded from both sides, I actually don't know whether this would work. That's a good question. Yeah. So like ratio data.
Yeah.
Yeah.
We just use beta regression.
I don't know.
Like an inflated.
Well, there are people who advocate not deal with ratio data as outcome. You want to pick up the numerator and denominator and model the numerator separately. Because ratio messes up things. But I don't know.
Any other questions?
Questions online?
I don't see any questions online. Okay, with that, thank the speaker. Thank you.